Good day, guys. Still on electricity. We have discussed some part of electricity in our previous class. So we have other things in the same topic that was repeated. And today we shall be looking at all these things on the board under electricity, which is going to be the concluding part of our previous class. So in our previous class, I have discussed electric field, I discussed capacitor, I've discussed some other things that has to do with electric field. I've also discussed magnetic field. I've also discussed electromagnetic field. And I've told you how important electricity is in the generation of magnetic field. I also taught you how important magnetic field is in the generation of what? Electricity. So we shall be looking at what we have on the board today. One of them is called equipotential surface. We shall be looking at, there is a surface in science called equipotential. We shall be looking at the meaning. Also, we shall be looking at the relationship between electric field and electric potential and electric field intensity. So these are three things we shall be looking at, the relationship. How does one of them work with other? So there is a relationship between the three of them. We shall be looking at it in a very simplest or simple way. So we shall be looking at something called electrostatic potential energy. P for potential, and this is energy. We shall be looking at that one as well. We shall be looking at electromotive force. We shall be looking at Kirchhoff. We call it, some people call it Kirchhoff, but I pronounce it as Kirchhoff rules. There are two rules for this man. One of them is called current, and the other one is called voltage. So we shall be looking at it. Then we shall be looking at a circuit that has to do with resistor and capacitor. We shall be looking at that as well. So this is going to be the concluding part of our discussion in electricity. So let's go back to the first one. If I have a surface, let's assume this is a surface, an electric surface, and I have point A, and I have point B, and I have point C on that electric surface. So if the electric potential at this point is equal to the electric potential at this point, is also equal to electric potential at this point, then this surface is called equipotential surface. So we can define it as equipotential surface is a surface where the electric potential at every point is equal. So go back to the diagram again. Point A, point B, point C. So electric potential V here must be equal to electric potential V here must be equal to electric potential V here. So which means if you are taught or you are told that electric potential at point A is 20 volts, and the current line say what is the electric potential at point B? Of course, it was 20 volts, and that of C2. So that is why we call it equipotential surface. It's an electric surface, or I call it electric plate, where electric potential at every point on that plate is equal. Now, having taken that definition, there are some properties we must know for this electric potential. One of the properties is that no work is done. No work is what? Done. Why? The electric potential at each of the points is equal, so we don't need any work done here. So mathematically, if I say no work is done, we should remember that in mathematics or in physics, we have this work done equals to QV in physics. Because if you define this, we call this one electromotive force, and some people call it EMF, some people call it potential difference. It is energy required in moving charge around the circuit. If this is regarded as electromotive force, then we can define. So by the time we get there, this is the definition we have for you. Electromotive force is the energy required to move energy, meaning work done, required to move charge. So I am moving charge, I am using work energy to move charge throughout the circuit. Now, if this is correct in physics, then by making W the subject of the formula, I will get in this. Do not forget what I want to show. I want to prove that In equipotential surface, work, there is no what? Work done. Which means work done is what? Zero. That's the meaning. Now, if this is correct, then I can have this. Now, the work done that I want to prove to be zero is equals to Q times change in V. I'm using this equation now. What is the meaning of change in V? Either V want to decrease or increase. V has changed. But going back to that definition, I have told you that V remains constant. So which means V is not what? Changing. So I can say change in V is equals to what? Zero. Or V is not changing. So I can have work done is equals to Q times zero. And anything times zero in the calculation is also, we can now say work done is equal to what? Zero. So I have been able by calculation or by formula prove that work done is what? Zero. So one of the idea of property when a surface has equal potential, electric potential, one of the property of that surface is that there is no work done in that surface. And that is how we can prove that work done is always what? Zero. Another property we must know for this is that the electric field must be perpendicular to the electric potential surface. Perpendicular must it form angle 90 to electric potential surface. What do I mean? Electric field, don't forget that all these are also being derived from electric field. So when this surface is brought to the electric field, so the line of electric field is like this. So the line of representing the electric potential surface will be what? Like this. And if the line representing electric field is like this, the one representing electric potential surface must be what? Like this. So between the electric field and the surface of electric potential, there is angle 90, and that 90 is what I call perpendicular. So those two properties are very important when we are talking about electric potential surface. Now, I am done with that. I am coming back to calculation. So let me just print all of them, then I take the calculation generally. Now, we shall be looking at the relationship between electric field, 1, electric potential, 2, and then electric intensity. Now, by definition, let's go into it. Electric field is a region or space where a charged body feels electric force of attraction. We have discussed that one previously. I repeat again. Electric field is a region where a charged body, this is a charged body. So all this region, this charged body will be feeling some force or some forces of attraction. So which means if any other object is here, carry charge as well. But this time around, this one is carrying positive and this one is carrying what? So there is going to be a force of attraction between both of them. Because this one is operating within the field of this one. And this one too is operating within the field of this one. But if the charges look alike, we are going to see a force of repulsion. So what am I trying to say? A charged body, we always feel a force of attraction or a force of repulsion when that charged body is going or getting through the electric field. So electric field is a region. This region where the force of attraction in this region attracts this object or repel it. It's going to attract if the charges are unlike. They are going to repel if the charges are alike. So then that's the definition. I'm coming back to the relationship, but that's the definition. Now let's go to electric potential. How do we define electric potential? Electric potential is the energy. Electric potential at a point is the energy in bringing a charge from an infinity back to the point. Let's assume I have this charge body. Then anything that will bring another charge body back to any of these points A, B, or C. Energy required to bring any other charge from infinity to either point A or point B or point C. So the amount of energy, if you want to drag something, you have to use some energy. So the energy required to drag a charged body from infinity, from a place very far we don't know, to any point, either point A or B or C, is called electric potential. So we shall proceed in the next class.